Hello everybody and welcome to the next video in our series of lectures. This one, Lab 10, involves torque. Torque is the rotational version of force. It depends on how far away from the rotational pivot you apply the force. An easy way to understand that is to just extend your arm and press down at certain points. The farther out you get, the harder it gets to resist it. So the simple equation in your textbook is force times distance. Again, that distance is the length from the pivot that it's rotating around. So we have two experiments today. One where we have various weights or masses at various points, and then we measure the force it feels. The other is using the concept of torque to get the mass of an irregularly shaped object that you would otherwise not be able to solve for. For the second part of the lab, this uses the fact that a stationary object will have the torque at all of the different points being equal and opposite so that it's not rotating. So for the first part, a key and a crucial aspect for this lab is that this must always make a 90-degree angle. That's why we have our little level here. It's quite simple. All we do is, based on the lab manual, we have a 500 and a 200 to make 700, and we place them in the various ringlets. And every time you place them out, as they get farther and farther away, the net torque increases and it pulls this down. And every time you change the mass or you change the distance, we would change this so that it remains roughly level again, making that 90 degree. That way we can use our trigonometry. Then we simply record the force up here, such as at this ringlet for 500 grams we have 11 newtons. Then we solve or plug in our values to solve for the various aspects. In your lab manual, you have the counterclockwise torque as well as the clockwise torque. It's important not to get those mixed up. You also have a couple of different radius. You have the radius of the ringlets. All of the radius go from where it's pivoting, from this point. You have the radius of the ringlets, as well the radius that the counterclockwise force is pulling from. That's going to be this string. That string extends imaginarily out into the middle of this bar where the black dot is. So make sure that you record those properly, or will record them. Make sure you use them properly in your result part. So it's fairly simple. We would just, if you did it yourself, you would just add the masses and repeat for all the different steps, making sure to keep this 90 and a potential source of error, making sure to offset in case the Newton scale does not reset back to zero. As you can see here, it's slightly off by about half a Newton. On to the second part with a irregularly shaped object. Any object, the mass is going to be focused at its center of gravity. So the center of gravity is roughly here. It's, on the larger side since it's a wedge. And when the center of gravity pulls down at the 2 points here and here, they feel their own torque. These two torques are equal and opposite to each other, which you can see by the fact that it's not rotating. We can use the fact that the two torques equal to find the total net mass. For this equation, or for this experiment, using the equation, using the equations for counterclockwise and clockwise torque, we would set it up as such, where we take the mass of one side, which is recording the effect of the torque here, and then we would turn it around and then measure the mass of the other side, which is, as a net effect, taking the torque over there. And then we simply add the two together and we get the total masses. And this can be used for any irregularly shaped objects in your lab manual. It gives an example about a truck with 4 wheels. So you can use this with 2 pivot points, you can use it with 4 pivot points, however many you want, so long as you keep everything in check. That should be it. Have a nice day.